So now let's do an example of solving a system with a general non-diagonalizable matrix. So we have the system y prime equals 2, 1, 1, 0, 5, negative 1, 0, 1, 3 times y. And we need to find the eigenvalues. So I'm going to take the determinant of a minus lambda I. So that's the determinant of the matrix. 2 minus lambda 1, 1, 0, 5 minus lambda negative 1, and 0, 1, 3 minus lambda. And I can actually expand that around the first column so that I get 2 minus lambda times the determinant of the matrix 5 minus lambda, negative 1, 1, and 3 minus lambda. So in fact, that's going to give me 2 minus lambda times 5 minus lambda times 3 minus lambda minus a negative 1. That determinant we're going to want to set equal to 0. So this is 2 minus lambda times, let's see, we're going to get lambda squared. Minus 3 lambda minus 5 lambda gives me minus 8 lambda. Plus 15 plus 1 is plus 16. Setting that equal to 0. And so, in fact, this is actually going to be 2 minus lambda times lambda minus 4 quantity squared. So lambda, in this case, is 2, and then there are 2 repeated eigenvalues of 4. So now I'm going to find the eigenvectors. So if lambda is equal to 2, then I want to solve the problem 0, 1, 1, 0, 3, negative 1, 0, 1, 1, times x equals 0, 0, 0. I'm going to row reduce this matrix to get 0, 1, 1. I'm going to take the second row and subtract 3 times the first row so that I get 0, 0, negative 4. And then finally, I'm going to get take the third row and subtract the first row to get all zeros on the bottom. Okay. I can take the second row and divide by negative 4 to get a 1. And so I can reduce this matrix one more time to get 0, 1, 0 by taking the first row and subtracting the second one, get 0, 0, 1, 0, 0, 0. Again, the right-hand side is 0, 0, 0. So my eigenvector is actually going to just be 1, 0, 0. Now I can look at when lambda is equal to 4. Plug that in for my matrix here. So I'm going to get negative 2, 1, 1, 0. 5 minus 4 is 1, negative 1. And then finally I'm going to get 0, 1, 1. Put zeros on the right-hand side here. Now I need to row reduce. So I still get a negative 2, 1, 1, and the right-hand side of 0. And then I'm going to take the second row, and it already has a pivot, so I like that. So I'm going to look at the third row, and the third row is in fact going to look like 0, subtracting the second row, 0, And 1 minus a negative 1 is going to give me, oh, I see what the issue is. The last row here, when I take 3 minus 4, is going to give me a negative 1. That makes more sense. So now I'm going to get 0, 0, 0 on the bottom row because those two rows are the same. Okay. So at this point, I can take the first row and I'm going to subtract the second row. So I'm going to get negative 2, 0, 2. And then I have a 0, 1, negative 1 there, and 0, 0, 0. So that the last row is all zeros there. And then from this point, it's pretty easy to see that if I let V3 be a 1 for the free variable in that third row, then V2 would have to be 1. And then, X2, the second row would have to be a 1. And then the first row would have to be a 1. Okay, so you can double check if you'd like that I can multiply the original matrix by 1, 1, 1. And in fact, that's going to give me the correct eigenvector. Okay, I multiply that matrix by 1, 1, 1, and I'm going to get all zeros. This is actually, sorry, this is V2 is going to be 1, 1, 1. Okay, now I would like to do the generalized eigenvector that goes along with lambda equals 4. So what I need to solve here is going to be negative 2, 1, 1, 0, 1, negative 1, 0, 1, negative 1. But the right-hand side now is going to be 1, 1, 1. So what I can do here is the same steps that I did before. So I'm going to get negative 2, 1, 1, 0, 1, negative 1. The last row is the same as the second row, so I get all zeros. And so that's true on the right-hand side as well. And then I want to do the same thing that I did before. I'm going to take the first row and subtract the second row to get negative 2, 0, 2. Okay, so I'm going to take the first row, subtract the second row, so I'm going to get a 0 on the top here. Then I'll have a 0, 1, negative 1 with a 1 there, and then I've got all zeros again. So again, x3 is the free variable, so the third row has that free variable in there. Okay, so I'm going to say x3 here is a free variable. And whenever you have a free variable for one of these generalized eigenvectors, we're going to set that free variable equal to 0 because we have a choice, so we're going to set it equal to 0. Okay, so the rest of the equations, as you can see, look like negative 2 x1 plus 2 times x3 is equal to 0. So in fact, x3 is 0. So that tells me that negative 2x1 is 0. So that tells me that x1 has to be 0. And then the very next equation is going to say that x2 minus x3 has to equal 1. But in fact, x3 is 0. So that tells me that x2 in this case is 1. And so my generalized eigenvector, which I will call W, is in fact 0, 1, 0. Well, that now gives me my similarity transformation because my matrix P is in fact going to be the matrix with the eigenvectors 1, 0, 0, 1, 1, 1, and 0, 1, 0. So those three columns are V1, V2, and W. Now the inverse, I'm going to leave up to you to find. But in fact, it happens to be 1, 0, negative 1, 0, 0, 1, and 0, 1, negative 1. And then you can verify what the Jordan canonical form is going to be, but it should be 2, because the 2 there corresponds to this eigenvector being first. And then the next 2 entries on the diagonal are going to be the 4s. They correspond to the eigenvector and the generalized eigenvector that correspond to 4. And then there's going to be a 1 there in the middle between the 2 4s. So that'll be the Jordan canonical form. So I leave it up to you. You should verify that either you can A is equal to P, J, P inverse, or that J is equal to P inverse AP, whichever you like. Now, so that means we need to solve Z prime equals J times Z, but in fact, we solved that problem before. That was actually the matrix at the beginning of the first video. In fact, we saw that the solution Z, it looks like C1 e to the 2t and C2 e to the 4t plus C3 t e to the 4t. And then finally, we have C3 e to the 4t. So that was our solution to the very first problem. And so y is equal to P times Z. So that's equal to the matrix 1, 1, 0, 0, 1, 1, 0, 1, 0 times Z. For convenience, I'm going to copy and paste this. And in fact, that will give us C1 e to the 2t plus C2 e to the 4t plus C3. I'm going to move this over real quick. So C3 times t minus 1 e to the 4t. So I'll leave it up to you to do the matrix multiplication. Okay, so then the second row will be C2 e to the 4t plus C3t e to the 4t. And then the third row is going to be C2 e to the 4t plus C3 times t minus 1 e to the 4t. And so in fact, that is going to be our solution, P times Z. And so that does look incredibly long, but that is the method by which you can solve a non-diagonalizable system of differential equations.